可以了吗
？OK， 好，
可以了哈。好，那我们已经2点。好。好。So, good afternoon, everyone. So, it's my great pleasure to invite this special speaker of this special seminar, Professor Zhonghan Li, to give his talk here. And let me briefly introduce Professor Li's scientific career. He got his master's degree in our neighboring university, Tsinghua University, 2010, and I co-advised back then Mr. Li, Master League seasons, and then after 2010, he served the military service and went to the U.S. Florida State University for a PhD until 2017. He got his PhD in condensed matter theory, working on DMFT, dynamical mean field theory approach to correlated electron systems. And after that, he spent almost 6 years at Rutgers University as a postdoc, working with well-known condensed matter theorist Professor Gabby Cochlear, again with DMFT related approach to correlated electron system. And then this year, he got a faculty position in Zhongzheng University in Jiayi, and as assistant professor, and now it's here. So Professor Li's expertise is in condensed matter theory, especially strong correlation effects, and he is an expert in numerical approaches to those correlated electron systems. So including the modified version of Slave-Boson theory that we will tell us about, and also the extended DMFT and so on. Okay, so let's welcome Professor Li.
Yeah. So thanks for inviting me here, and yeah. So so today I'm going to talk about this approach that is called GhostRotationally-Invariant Slave-Boson approach. And I hope that in the end, I can show you that it is efficient and also accurate approach if you want to study strongly correlated material. And this work was done mainly in Rutgers University that I have done my postdoc research. And it is supported by Department of Energy. So okay. So I will start from the strongly correlated material, where in this type of material, the electron strongly interact with each other through Coulomb interaction. So there's the electron spin, charge, and orbital degrees of freedom intertwine strongly with each others. And it often can lead to this kind of complicated phase diagram. For example, here I take this calcium strontium oxides. So in this material, if we dope this with from the calcium to strontium, or increasing the temperature, they will have a different type of a transition, either from magnetic ordering state to non-magnetic ordering state. And there are also metal insulator to insulator transition. And most interestingly, in this material, there are also many material has these unconventional superconductivities. For example, like the cuprate at the 80s, luthenate in the 90s, iron-based around 2000s, and recently nickel-based, and this controversial LK99. So it's interesting that there's a pattern that's like a new type of superconductors are discovered like each decades. So the problem is that this type of a strongly correlating material is very hard to describe by the standard density functional theory or any kind of a single particle approach. Therefore, it is very important that one has to develop many-body approach to be able to have ability to study the physics in this material or even to predict their properties. So the approach, many-body approach that I have been working on is based on this quantum idea of quantum embedding. So we all know that it is very hard to solve interacting lattice problem, exactly because the size of the Hilbert space grows exponentially with the number of the sites and the number of the active orbitals each atom. So the idea of quantum embedding is that instead of solving just the entire lattice system, we can pick one atom and then we treat it like impurity. And then the rest of the atoms, we can view them as an environment. And we can map this interacting lattice problem into this kind of quantum impurity model. And then the idea of quantum embedding is that we will match certain quantities in these two systems and until they reach some kind of cell consistency. And then we can use these quantities to analyze the physical properties of these original interacting lattice systems. So there are many different types of approaches that is based on this idea of quantum embedding, which including this very famous dynamical mean field theory. And there are also Slave-Boson approach, which is equivalent to Wheeler approximation, which can also be formulated into this quantum embedding type of the framework. And there are also this type of this self-energy embedding theory and this DMET, which are more widely used in the quantum chemistry community. So this dynamical mean field theory is the most popular and the standard way to in this quantum embedding framework. So in the DMFT, one will assume that the self-energy is local. So we will not have a momentum indexes here in the self-energy. And with this type of approach, we can map this interacting lattice approximately to a quantum impurity model where we have this self-energy of the impurity. And this is the hybridization between the impurity and the bath. And the cell consistency within DMFT is that we will require the local Green's function of this impurity lattice has to be matched with the local impurity Green's function in this quantum impurity model. And once we have this convergence of the Green's function, then we can use this self-energy and Green's function to analyze the physical and electron properties of the original interacting lattice. So it turns out that this DMFT approach is exact theory in infinite dimension in this kind of imagined artificial lattice. And so it works well if we are studying the system with a large dimension, or the spatial or quantum fluctuation is less relevant. For example, at high temperature or away from quantum critical points. So in this region, DMFT is a very good theory to predict the property of these systems. So the early DMFT result is mainly focusing on this Hopper model, which is one of the standard model to study strongly correlated physics. And we have this hopping term describes the hopping of the electron from site I to another site I plus 1, nearest neighbor. And there's another Coulomb interaction term describes the on-site Coulomb interaction. So we can imagine that if the system is half-filled and there are atoms on each site, then if there's another atom hopping from a site to another site to create this kind of double occupied configuration, then this U term, if it is very large, then it will cost a lot of energy. Therefore, when we have a very strong Coulomb interactions, this double occupied configuration will be not less favored, and the electron will instead like to be localized on their own sites. So the system, the electron in the system will not like to hop around, and it will become an insulator that is called mud insulator. So DMFT is one of the most successful theory to describe this type of metal to insulator transition as one tuned on the Coulomb interaction. And there is no structure or magnetic transition as the system transformed from metal to insulator. So here it shows the DMFT density of state. And we can see that at the small interaction, U equals to 1, we will have a very broad conduction band around the Fermi level. And as we start to increase the Coulomb interaction, then we will have this additional high energy excitation emerges that is due to the fluctuation of the atomic orbitals. And we will have this narrowing bands at the Fermi level become narrower and narrower, indicating that the electron effective mass becomes very small and they become very localized. And once we pass through the critical interaction, we will have a gap and the system will become an insulator, which is known to be a mud insulator. So this scenario works very well if we want to study this type of vanadium oxide for the insulator to metal transition. So as we apply pressure on this material, then we can see that there is a transition from insulator to a metal, and there will be no structure or magnetic transition. So DMFT is one of the theory that can capture this type of insulator to metal transition without the needs to break any kind of symmetry. So nowadays, DMFT is usually combined with the density functional theory. And it is very successful if we want to study correlating material. For example, here I showed these APES data, which are the dots here in red, and the background is the DMFT plus DFT plus DMFT calculation. And we can see that the agreement between DFT plus DMFT with the experiment is quite good. So it is quite successful if we want to study the electronic structure for this interesting correlating material with superconductivity. And it can also be used to compute the spin excitation, for example, the spin susceptibility observed in the neutron scattering for this heavy fermion compound plutonium. And here it shows the spin excitation as a function of the momentum and the energy. And here it is the observed spin excitation energy scale, which is also agreed quite well with this DMFT calculation. And very recently, it is also possible to compute the phonon for this correlated iron-based superconductor. And the dots here are the experimental observation. And here we again see that DMFT capture quite reliably the phonon dispersion in this iron-based superconductor. So it works very well, but it is also known that DMFT is very time-consuming calculations. So in order to get this type of results, typically one has to use the quantum Monte Carlo impurity solver, and you usually requires like hundreds of CPUs, and sometimes depend on the calculation that one needs to carry out, it may take hours to days of the calculations. So it is not very feasible if we want to study, for example, more complicated type of the material with more atoms. And also, we cannot able to predict high throughput calculation in order to predict the properties of correlating materials. So this leads to my recent efforts that we would like to develop alternative methods that is more efficient, but at the same time, it has the relatively smaller computational cost if we compare to DMFT. So this approach is based on this idea, this method that is called rotationally-invariant Slave-Boson. And it is designed to solve multi-orbital Hubble model, where at each sites we can contain, for example, here 5D orbitals or 7 orbitals if we want to consider heavy fermion system. So to get this, to describe this multi-orbital in this Hubble model, besides the hopping T and U, we have these additional indexes M and M prime that is labeled, that labels the orbital degrees of freedom on each site. And we also see that the Coulomb interaction now is a tensor instead of just being a scalar. So the idea of this particular Slave-Boson is based on mapping. For example, we focus on the local Hilbert space of an atom. We call it A. Then we will map this local Hilbert space of one atoms into a product of the boson state that is described by this bosonic operator phi acting on the vacuum. And we see here that this boson operator is a matrix where one of the index corresponds to the local Hilbert space, and another corresponds to this a copy of the local state that we call it as a quasi-particle Fock state. And we use this F to label this quasi-particle degrees of freedom. So within this type of mapping, the original electron can be written in terms of product of boson operator R, which is a matrix, and as is a function of these boson operators. And this matrix is product to these quasi-particle Fock states. So this is the form of the representation of the original physical operator in terms of boson and fermion. And because we have enlarged our Hilbert space to be a product of the boson and fermionic states, we have to apply this constraint so that our solution will live in the physical states. And the first one requires that the boson amplitudes or the occupancy has to be 1. And the second one is a gauge constraint that when we perform a gauge transformation simultaneously on the boson field and the fermionic field, the entire Lagrangian, if we write it down, will be gauge invariant. So with this, we can now write down the Lagrangian, but I will not go into the detail, but I will just give you a schematic results after we perform the derive the settle point of this Lagrangian. And in the end, we will have this quantum embedding picture for this rotationally invariant Slave-Boson. So in this framework, we will map this interacting lattice into a non-interacting lattice where which is called quasi-particle Hamiltonian, and we will have this R describing the hopping of the electron from site to site, and this hopping term will be renormalized by this factor R, and we will have this one-body potential lambda that is approximated potential of the local interaction, and this determines the this quasi-particle Hamiltonian. And we will also map this interacting lattice to this impurity model. And we can see that different from DMFT, our environment is approximated by just an atom, and which has the same number of the orbital as the impurity. And so this D describes the hybridization between the impurity and the environment, and the lambda C describes the potential on this environment atom. So, and the self-consistency condition with our RIS approach is that we have to match the density matrix of this non-interacting Hamiltonian and the density matrix of this impurity, quantum impurity dimer. And so here the delta is the local density matrix on this non-interacting Hamiltonian, and it has to be related to the density matrix of this Betz atom, and also the hybridization between the impurity atom and the environment atom. So another key difference of our approach is that in our self-consistency condition, we don't need to compute the Green's function or self-energy, which will require us to compute the excitation or excited state. Therefore, we only require to compute this static density matrix, and which will make our algorithm more efficient. And another efficiency comes from this impurity model, where we only need to solve these two sites impurity model instead of Anderson impurity model, which also makes this approach highly efficient.
Yeah. Ask a question.
Yes.
So you each orbital then you decouple CN operator to the product of the whole spin out like this, and you use a rotation label.
Yeah. So if we view it in a one-band place, we can view this as a spin-out, and this could be holon or doublon or single occupied boson excitation. Yeah. So, but in the multi-orbital space, this boson will contain more different type of atomic excitation, which is described by this 5 boson algorithms.
So can I ask you another question? So
yeah,
in the next page, so by doing this Slave-Boson representation of the conduction electron C, and the interacting lattice becomes non-interacting.
Yeah. This is like a quasi-particle. Yeah.
So you're saying that the upper U is gone.
Yeah, it's described by this, approximated by this lambda that we have to determine self-consistently, but it exists in this impurity model where we still consider this correlation effect from this part of.
So is this similar to the infinite U Anderson impurity model? When U goes to infinity, you could use Slave-Boson to rewrite your Hamiltonian, and then this Anderson U term is gone.
Yeah, probably not exactly the same, but yeah, because we didn't take U to the infinite limits. Yeah, but it comes from the settle point Lagrangian, which I can show. But
in your formulation, this rotational invariant Slave-Boson approach, does U appear or not?
Yeah, it appears. Yeah, it will appear in the Lagrangian as living in this impurity space. So basically, our Lagrangian will have a space that is corresponds to the quasi-particle space, and another space corresponds to the boson degrees of freedom that is described by this impurity model. After we perform some mapping, those boson field can be become some kind of wave function of fermionic Hamiltonian. Yeah, so we have this Lagrangian, it contains these two terms and some coupling terms that links these two systems, and which will correspond to our self-consistency condition. Yeah, and if you are interested, I can show you. Yeah.
Can you tell me a little bit more about the non-interacting part? I take it that since there's R and lambda, it's in terms of Slave-Bosons.
R and lambda can be viewed as type. Lambda is a Lagrange multiplier that enforces this.
Right, but it's a non-interacting Hamiltonian formulated in terms of these pseudo particles.
Yes, pseudo particle.
With a constraint.
With the constraint, yes.
So it's actually not a free Hamiltonian.
Not a free Hamiltonian. You have to, determine through this cell consistency.
And since the constraint is local, in principle, you would have on each side of your free Hamiltonian a constraint.
Yes.
Not a global constraint.
So on each side we have constraint, and you say it is not a.
You have to enforce it's local. So on each side you would have a different lambda. You would not have just two constraints from before, but 2 times the number of lattice sites.
Yes, but but here we assume that it is spatially uniform.
Okay, so there's an additional.
This is So that the R and lambda are all constant, but in principle we can also do non-homogeneous system. You just take another more complicated calculation, but not very heavy.
So I assume that you are getting a dispersion, which you are not getting in the DMFT. The bare dispersion is usually fixed in the DMFT, isn't it?
The dispersion, so for us, we can only get a narrowing of the bands around the Fermi surface. And we could not get a higher and lower Hopper bands within this framework. So this is what I would like to address later on with our new development. But we can show the comparison between our discussion with DMFT later. So this is the approach that we will use. So it is quite efficient. So you can also combine with DFT, and it is very successful if we want to study, for example, the total energy of the heavy fermion system. And here in this Praseodymium system, there will be a transition from alpha uranium type of structure to FCC as one compressed system. So the volume will become if we compress the system, the volume will become smaller, and we can calculate the energy as a function of the volume. And we see there's a crossing between these two phases, and meaning there's a transition from alpha uranium type structure to FCC. And if we do the derivatives with respect of this E to the volume, we can get the pressure versus volume curve. And here the dot is the experiment, and it shows that this LDA plus risk, which is equivalent to Gutzwiller, gets quite nicely this equation of states curve. But if we want to study the Mott transition and we apply this approach to these oxides, which these three are known to be Mott insulator, and we found that if we use the realistic constraint RPA approach, the Coulomb parameters calculated by constraint RPA, and we can see that for iron oxide and copper oxide, we cannot get a quite reliable unit cell volume for these two materials. And also in the experiment, which are the circle here, it is known they are in the insulating phase, not insulators. But in this RIS approach, we predict them to be metal, or we got a metal solution. So to solve this, we have to use quite large and unrealistic Coulomb parameters, which corresponds to the on-screen Coulomb interaction. in order to get a good agreement with the experiment. So we believe that it is the oversimplification of this risk multi-insulator transition scenario, where left-hand side is the DMFT, where there's a metal to insulator, and there's two mud bands here in the insulating states. But instead, in this risk or almost all kind of Slave-Boson approach, in the mean field framework, we can only get a renormalized spin quasi-particle peak, and in the insulating state, there will be no density of states. So this type of transition is known to be the frequent rise metal insulator transition scenario, and obviously it violates the sum rule of the spectral function, which if we integrate it, it has to be 1. And therefore, it is also expected that it is quite inaccurate if we want to calculate the kinetic energy.
You get a maximal violation? You get 0 instead of 1? Or?
Yeah, we get 0 in the buffer, so it's very bad. But yeah, so that's why the energy doesn't work quite well, and we cannot get a very reliable critical U here for the mud transition. So now this leads to our recent work that we try to use this ghost risk approach to try to improve the accuracy of this risk approach. So previously we say that the quasi-particle fermion and the electron has the same number of the orbital, and the R matrix is a square matrix. So in the one band case, we will have one orbital here, and this become a scalar. So we can only describe one single band around Fermi level, and then we become smaller and smaller because this renormalization factor. And then when R goes to 1, then we will not get any quasi-particle dispersion. So, and here recently we found that with the approach that is called ghost approach, that the idea is to add additional quasi-particle into our Slave-Boson framework. So we will enlarge the number of F here. So we will enlarge the quasi-particle Fock states, but still this phi matrix of the boson, the A still lives in the physical space. So this phi will act like a projector that map the enlarged Fock state back to the physical states. And we found that by adding this additional quasi-particle into these quasi-particle Fock states, this additional quasi-particle, for example, if we add 2 additional quasi-particle, these 2 quasi-particle can allow us to capture the higher energy Mach excitation in the spectral function. And the consequence is that now this R and phi can be viewed as some kind of projector that you will map these enlarged Fock states back to the physical local Hilbert states. And this R will also map the enlarged F quasi-particle orbitals back to the physical operator through these 2 projector. So this is the main the modification of the original risk, and the rest of the settle point equation and the constraint still remains the same. And so in this quantum embedding scenario, because we have added additional quasi-particle fermion into our system, so our quasi-particle Hamiltonian will include these 2. For example, if we add 2, then we will just have these 2 additional quasi-particle. And then in the impurity model, the quasi-particle orbital will go to the environment, and the rest of the self-consistency and the Lagrangian still remains the same, except the R will become a rectangular matrix and lambda will be enlarged because we have more quasi-particle degrees of freedom.
Now, before you had 1 peak, now you have 3 orbitals.
Yeah,
3 peaks.
3 peaks, yeah.
What if you add 17?
Yeah, so these will come next.
Okay.
Yeah. So this become very interesting. Then we can add more and more and more. And then this 2-side dimer will evolve into this DMFT like of the Anderson impurity model, where the path will be continuum. Therefore, we would like to see like our risk will approach to these DMFT limits, which is exactly in infinite dimension. So as Professor Kutcher says, then we add more and more from 1, 3, 5, 7. Now we can see that in 3, this is the double occupancy and total energy. And we see that with just 3 orbital, we get a very accurate total energy and the double occupancy. And if we keep acting, we will observe that they will converge to the exact DMFT limits. And we see the convergence is better if we compare to DMFT with the discretized number of the bets. And we also see that this G-RIS approach is kind of satisfy the variational principle, where the energy converge to the exact value from above. And furthermore, we can also check the spectral functions. And as we add more and more, and we can see that we can start, we have this spring parameterized without the upper bands. With 3, we get 3 peaks structure, and then keep adding, then we will get more high energy excitation. And it seems to agree quite well, again, with the DMFT calculation. And within this calculation, we don't need to perform, our Green's function has this analytical form, and we just need this converged renormalization matrix and the lambda in order to get these Green's functions. So this summarizes this approach in the 1 orbital simplified Hubble model. And here we also try to combine this approach with DFT to simulate more realistic materials. And the idea is like here, we have this DFT constraint equations. When we solve it, we can get a band structure. And then we can pick energy windows by selecting several bands in this band structure, and then construct some low energy Hamiltonian, which is the hopping term and the U tensor. And we can construct this interacting lattice model. Then this interacting lattice model will be solved by our GhostRotationally again. And then once we solve this approach, we can compute the charge that contributed within this window, and then embed it back to this DFT part, and we can loop this circle until we have the convergence of the charge density. And here, this is the charge self-consistent, meaning the charge converged, LDA plus G-RIS calculation for this correlating metal and this Martin-Schlatter material with a realistic Coulomb parameters. And it is the energy as a function of volume. And we see that original LDA plus RIS is quite far from the DMFT, which is the black line. But if we use our LDA plus G-RIS, we can get a very accurate total energy, which it just has a very small difference compared to DMFT. And in this nickel oxide, there's a big improvement in the energy because in RIS, we still got this metal solution, but within our correction of the ghost orbitals, we can get also quite accurate energy compared to DMFT. And here it is the spectral function for this nickel oxide where RIS has some problem. And we can see that in RIS with U equals to 10, we still get a metal leak solution with a band crossing the Fermi surface. But with our correction of the ghost orbitals, we can open up a Mach gap, and there will be 2 upper and lower Hubble bands which locate at the position in good agreement with the DMFT, except that because our approach is a mean field approach, so it doesn't have a finite imaginary power self-energy. Therefore, we cannot capture this type of smearing bands with finite lifetime. So this is one of the features of this approach, but overall the agreement is quite good. And so this I hope it showed that these two combination is a good marriage between these two approaches. So this is the conclusions of my talk. So I have introduced this juries. It's a relatively efficient approach compared to the dynamical type of embedding methods. And then we also show juries is systematically improvable as we including more and more orbitals into our ghost risk calculation. And as we have observed in multi-orbital and one-band case, the static observable generally converge faster with the increasing number of the Bethe orbital compared to DMFT with the Z diagonalization, solving with the discretized Bethe orbitals. And then also our juries is able to capture dynamical spectral function. Although it is a type of a static approach, it still can capture dynamical spectral properties. And then I show that DFT plus juries is quite promising. And if we want to study the total energy, and it can also capture quite decent spectral function besides of these smeared Hubbard bands. So this is the outlooks, some of the outlooks of our work. So this is just started now, and we have only used the Z diagonalization solver for our impurity model. So you would be interested to use, for example, tensor network, Monte Carlo, or other type of methods to solve this quantum impurity problem. And we can also compute the response function or pairing interaction vertex, and using some diagrammatic extension, which will be also interested. And recently, juries has also been extended to non-equilibrium system. And here it is the evolution of the double occupancy at half filling of the Hubbard model as a function of temperature. And the dots are the DMFT results. And we have applied a quench in the Coulomb interaction. And we see that if we increase the number of the Bethe orbitals, it also converges to DMFT value and capture quite good until some time when it becomes not so reliable. And it is also possible to do a correlated topological material, and because our approach is also very efficient, so it could also be applied to compute the forces and the phono dispersion for correlated systems. So here is the acknowledgement that I would like to acknowledge my advisor, Gabriel Cotier, and my PhD advisor, Vlad Bogosalevich, Nicola Lanata and Yongxin Yao. They are expert in Kutzwiller, and Corey and Ron they are helping me for the DFT calculations. And with this, I would like to thank you for your attention.
Questions and comments.
Yes. Look, when you notice that you are not getting the sum root, you're talking about it. I thought the first hint would be that one thinks the fermionic commutation relations are not correct because that's what enforces them. Can you see how the two are linked? That when you include more fermions, how this affects the fermionic commutation relations? Or don't they have anything to do with each other?
The sum rule here? Or... Yeah,
If you take a bosonic spectral function, there is no such sum rule because the commutator is not based on anticonvolution. It's the anticonvoluting that gives you that property.
Yeah, I'm not sure what would be how to connect this with the fermionic commutation relation, because
you're saying only commutation relation will give you some.
Yeah, I mean,
And that would complicate.
assume you have something like a matrix where you have a diagonal part, which is a standard. If I dagger fi something like this, and then if I have j combinations of diagonal, and you look at the spectral functions only on the diagonal. The off-diagonals will always have spectral functions which, when you integrate them over, is zero. That's a consequence of commutator, the one that you get in the anti-commutator, which is not there. Let's say you take a trace over some density matrix like this, it will give you n because of each diagonal, when integrated over, you get one.
I see.
So it's anti-commutational relation.
I see.
So my first guess was that something with the fermions is not quite right. But then I don't see how adding more local fermionic orbitals will affect it.
Yeah. So this part I am not quite sure. I have to think about it. But what we can see here is that the sum rule is violated. Is that if we integrated this Green's function, and when this R in the one-band case R become a number, and we know that the quasi-particle wave will goes to zero, and this is in the denominator. So when R goes to zero, we can see that the sum of the spectral wave goes to zero. Yeah, but I'm not quite sure how does it connect to it.
Can I think of this Green's function as a general resolvent? Meaning that when you say it's static, you mean that there's no dynamic self-energy because it's a general resolvent. In some sense, it's a general non-interacting problem.
Yeah. Kind of like, probably kind of like that. Yeah. Thanks for the question.
DFT people talk about DFT plus U. What's the difference between DFT plus U?
Oh, yeah. So DFT plus U can be viewed as a specific case of our approach. So if we solve, we don't include ghost, and we solve a dimer. And then if we solve this problem using Hartree-Fock, then we will get DFT plus U. Yeah, so it's kind of including our theory. Yeah.
You said the DFT gives you the one transition.
Yeah.
Now, I think I could get away by saying that the DFT does not get the correct one transition because the entropy on the magnetically ordered side is maximally wrong.
Right.
Does this have any consequences for the actual? So I know that one could say, oh yeah, I know it gives me compensatory order and the order. But if you wouldn't know that a priori, is there any indication that at the transition the DFT misses out on something? So I'm thinking of an argument that if I want to get the transition right, I should get the two phases right. But the magnetically ordered phase, the DFT is not getting. So how come that maybe in the charge sector where the mod physics happens, everything is okay, but in the magnetic sector, it must screw up.
So so that's one of the way that like one used the kind of like cluster of finite larger size of the correction to take into account the spin, like entropy and some kind of ordering or dimer like behavior, dimerization behavior, and and you say that if we can know a priori if DMFT work well.
I don't know. Look, I mean, if Kotlin would be here, I wouldn't say it like this because he would shout at me. Because people are very defensive of these things, but maybe people don't say it, but I think everybody knows that magnetically ordered side you get a macroscopic entropy, which is not there. Zero. And so I don't know whether this has any consequences.
this what I know is that would change the slope of the this transition. So the shape of this slope will depend on the entropy in the low energy part of this transition. So, for example, if the insulator has some ordering, then it will lower probably the entropy in the spin part of then due to this Maxwell construction, then there will be more bending here. So that's one of the consequences that I can see. And I think generally DMFT doesn't work well if there is some kind of spin-spin correlation at low temperature. Yeah.
How is it in neutral? So I saw that the title of the PX was you're looking at the pair susceptibility.
Yeah, we can calculate.
Could you do the spin susceptibility, or is there?
Yeah, we can calculate all kind of susceptibility, and we would like to. But those are for only the RISC original formulation, and later I would like to test it with this, testing with our ghost extension and to see if it also improves this kind of spin susceptibility.
Can I ask one more question?
Yeah.
What if you have a long range detection? So it's something that is not entirely local, but that is more like, let's say, a Kalikov-Kimball kind of term. So you couple to the local physics to part of the electron.
Oh, you mean like a Kondo type, or?
Not like a hybridization, but let's say I get a term that says the local occupation times the occupation of the conduction electrons nearby. So that's particle gives me some extra energy. Something like you have in a very model.
I see.
For DMFT, I think this is hard.
I haven't tried that, but isn't it exactly solvable using DMFT? I'm not sure because I never worked on that model, but I remember I read paper they say it's exactly solvable if one uses DMFT.
So within DMFT, you get the self-consistency condition is an algebraic equation for the Green's function. It's not an integral equation. But it so that the Kalikov-Kimball model has an infinite number of conserved quantities. But I think it's not exactly solvable. It makes a difference. It's not beta that's solvable.
I see.
But depending on how you write the self-consistency, I think that the DMFT ruins this combination.
Yeah, I see. Yeah, I never work on that, but yeah, you would be interested to check if our approach will work.
More questions? Yeah, so I have a follow-up questions to Stefan's comments. So in the examples that you show, are they all kind of charge properties, right?
Right.
Like metal to insulator transition.
Yes.
And any spin degrees of freedom.
Yeah, I haven't included like magnetic ordering type, but yeah, it's also an interesting way. But usually, if we consider spin ordering, then LD plus U works pretty good. Yeah.
So is that fair to say that DMFT works well for the charge sector? At least there's no well-known problem with that. But maybe for the spin problem there is some.
I know the thing of the Mott physics, but usually people would say it captures the Mott physics perfectly, but
Kondo Mott, yeah.
But yeah, like within DMFT, Mott physics is Kondo physics.
Yes.
But if you go to clusters, not here this goes through.
Yeah.
But once you have a cluster, you break translational symmetries. So you get ordering which may not be there because you broke symmetry.
Yes.
Yeah.
What about experiments? So it's, I mean, your prediction from this ghost rings seems to agree with the experiment. Any
Yeah,
experimental data that it showed.
Yeah, so I think we could check the spin susceptibility or something like in the materials, but now I didn't compare. Yeah, so because I just started to do this, so
They're all theory. I mean, they're all theory.
Yeah,
Like any experiments on NIO.
yeah, there are some like RPS and there are some comparison
Does
which
the band structure look like this?
yeah, and they didn't get the entire band structure, but this some comparison with the XPS. Yeah, but this is not completely sure because it's we're still checking. But
XPS.
yeah, we're still checking, but it looks
Reasonably.
good. Yeah, but we still want to check. Yeah.
It does capture some experimental. It seems so.
Yeah.
So one more question. So what is the advantage of using this ghost?
Yes. Yeah, so the
Compared to the
advantage
NFT.
is the computational cost. Yeah. It's so we were using something that is not very optimized because we constructed from scratch. So, but still at this level, it compares quite good compared to.
So how much time that you could save compared to the NFT?
Yeah, so here is some like scales. Yeah. So we can do things on the laptop, but if we do DMFT, you have to do
5 hours.
Use clusters. Yeah.
Versus 30 minutes.
But it's not completely.
Okay.
Yeah.
Alright.
The first is only use space in
So
ACP.
so without code, it may be possible to do material with correlating material on the laptop, but usually DMFT, do you want Monte Carlo solver, then you need hundreds. Yeah.
When you add the ghost fermions, they are part of the constraint.
Constraint, yeah, they are
But in addition, in the free particle, Newtonian, they also come with atomic energy at least.
Yeah.
So how do you adjust those?
Yeah, so they are.
Does this come out, or is that a free parameter?
Yeah, they are kind of. You mean the atomic energy level? Yeah. So, yeah, they are coupled through determined through this. Yeah, so basically our so it comes into the energy. Maybe I show the saddle point equations. Saddle point equations.
Since we still have a couple minutes,
you
may just present some of the details.
Yeah. This is the Lagrangian, where this is the quasi-particle Hamiltonian. Yeah.
Magnify this. Yeah. Okay.
Yeah. So this is the H quasi-particle where hopping get renormalized by R, and lambda is the local potential. And then this is the atomic parts where we have phi, and these are atomic excitation. So basically, the rest of it are the constraint term, where at the saddle point they will cancel. So in the end, the energy will be just this hopping term and this potential term in the Coulomb contains all the excitation. Yeah, and. Yeah, this is some mapping that we can map the boson to some kind of fermionic Hamiltonian written in terms of the wave function. Yeah, but it's some detail, but yeah, the atomic information lives here. And if we want to study all the local atomic average, we can compute it within this place. Yeah, within the average of the trace of the boson.
So this phi is not a slave boson.
These are boson, Slave-Bosons. Yeah.
They are Slave-Boson.
Yeah.
I saw this capital R.
R is a function of these phi's.
Oh, okay.
So
R is
you
function of
have product
phi.
of
Phi
phi's.
Slave-Boson.
Yeah, phi are Slave-Boson. But R can be viewed as also a boson because it's all this combination of phi's. So it's quite complicated theory of goes. Goes to.
Then you solve the zero point equation.
We
So
solve this.
consistently.
R, the form of R is also quite ugly, so we promote R to become a independent variable, and then through this D. So the form of R would be, this would be in the denominator, and then sorry, I didn't write this part of the slides very nicely, but R will be, D will enforce the structure of R, so DD, so R will be this term divided by this inverse of this term, and this term will also be a function of the phi that is enforced by lambda c. So R is a very nonlinear function of phi with a square root or something. But this is the Lagrangian that we want to solve for the saddle point for all the R lambda phi d lambda c, and we can solve the saddle point equation, which is just this set of equation where we solve the density matrix of this non-interacting Hamiltonian, and then we have to diagonalize this diagonal problem, and then solve these sets equations consistently. But they are just like standard mean field type of equations.
If you now add fermions, if you add more fermions, you get more self-consistency equations.
We still get the same.
So there's a freedom.
We got the same set of equations, except R becomes rectangular and D becomes rectangular, and this delta P will enlarge because we have more quasi-particle, but the equations are still the same. So everything is unmodified if we add more and more fermions.
But when you add more fermions, is everything determined, or do you have a freedom to choose? I just want to know how you need things.
So the only things we need to choose is how many orbitals we want to add here. And all the constraint and things still all remains the same. So we just need to add more orbitals in here, and all the Lagrangian, everything remains the same. It's just the size of these matrices will be different, but they all remain within the same.
If I get more fermions, more unknowns, I get an equal increase in the number of equations.
Parameters,
Okay.
It become more complicated, but the equation is like this, and we can still solve it. Same structure.
I understand, but I want to know whether if you add a number of fermions, whether you have a freedom to work. But you're saying no, everything is.
Right. So we don't.
Add more constraint, right?
We have more constraint equation, but they can be formulated to this compact.
Same way.
Yeah.
One question. So where is the upper U here? See that?
So it's in this H local. It is actually many body operator. So H local, it contains U, F dagger, F dagger. So this F is the fermionic representation of the local F operator. So it lives in this H local here.
So you don't throw away the U, so I increase U.
No, it still lives in here, and all the local energy level interaction, it's all living in this local.
More questions? So let's thank Dr. Lee again. And have a free discussion.
Yeah.
Thank you for coming.
Thank you.
I will call you.